Hello everyone, welcome back to our YouTube channel Scratch Learners. Today we are going to discuss about Quicksort. So, what is Quicksort? We all know this is a sorting technique used to sort an array containing some elements. This Quicksort method is an efficient sorting technique that follows the principle of divide and conquer strategy. We already know whenever we have a large array, then it becomes difficult to sort the elements of the array. So here we are using divide and conquer strategy, in which we will divide the large problem into a number of smaller sub-problems, and then we will find a suitable technique so that each sub-problem can be solved quickly, and then we will combine the results of all solutions to get the final solution. So here in the step of division, in the beginning we will partition the list, that is the array A, which contains elements from the index 1 to n into two sublists. The first sublist containing the element from index 1 to p minus 1, and the second array containing the elements from the array from the index p plus 1 to n. That means this is the left sublist, this is the right sublist, and the position of partitioning is ap. That means the element of the array at the index p. So we will partition the list such that each element in the left sublist is less than or equals to AP, and each element in the right sublist is greater than AP. That means let this be an array. So if we want to position the element 5 in its sorted position, so here we have positioned the element 5 in its sorted position, right? Because all the elements in the left side are smaller and all the elements in the right side are greater than the element 5. In the same way, we will place all the elements of the array in their sorted position, and hence we will get our sorted array. So this was the divide part, and in the conquer part we will sort the two sublists, that is the left sublist and the right sublist, recursively until the sublist contain either 0 or 1 element. That means again in the left sublist we will partition the element, right? And in the right sublist we will partition the element, and these steps will be repeated recursively until we get each sublist containing either 0 or 1 element. Now let's try to sort this array using Quicksort. Here we are considering 8 elements starting from the index 0 to index 7. So what is our aim in this method? Our aim is to place each element in its sorted position. That means the position in which all the elements in the left part will be smaller and all the element in the right part will be greater than that element. So here the element which we want to place in its sorted position is named as pivot. Okay, so here we can start considering the pivot as the first element or the last element or any random element, right? So here I am considering the pivot element as my first element. Okay, so pivot equals to array at index 0, that is 5. Now we will take two index variables I and j. I will be initialized from low plus 1, that is 0 plus 1 equals to the index 1, and j will be initialized from the upper index 7. Okay, so we will start by comparing the pivot element with the element at the index I. Okay, and if the element at the index I is smaller than the pivot element, then we will increment the value of I, that is I moves from left to right, and side by side we will compare the pivot element with the element at the index j. If the element at the index j is greater than the pivot element, then we will decrement the value of j, so j moves from right to left. So whenever we want to place an element in its sorted position, we need to shift all the element which is greater in the right side, and we need to shift all the elements which are smaller than pivot in the left side. So this is how we'll do this. So the goal of index I is to get an element greater than the pivot element, and the goal of the index j is to get a smaller element than the pivot element. So we will start by comparing the element at the ith index with the pivot element. So is 9 greater than 5? Yes. So we will mark the index 1 as the variable I. Okay. So here we got an element which is greater than the pivot element. Right. Now from this side we will compare the element at the jth index with the pivot element. 12 is compared with 5. Is 12 smaller than 5? No. So we will decrement the value of I. Now 14 will be compared with 5. Is 14 smaller than 5? No. So we will again decrement it. Now j is 5 and the element is 3. So 3 is compared with 5. Is 3 smaller than 5? Yes. So this index 5 will be marked as the index j. Now what we'll do? We have found an element greater than the pivot element and an element smaller than the pivot element. Now we will interchange 9 with 3. That means the element at the ith index will be swapped with the element at the jth index. So 3 will come to this position. Then 9 will go to that position. And our array will look like this, right? So till now the value of I was this element, right? And the value of j was this element. Now we will again start comparing the elements. So now the value of I is incremented and the element 2 is compared with the pivot element 5. Is 2 greater than 5? No. So we will again increment the value of I and it will point to the element 7. Now is 7 greater than 5? Yes. So this will be marked as the element at the index I. And from this side we will search for a smaller element, right? So after incrementation of j it will point to the element 4. Now 4 is compared with 5. Is 4 smaller than 5? Yes. So this will be the element at the jth index, right? So we need to interchange the position of the ith element with the jth element, right? So we will swap both the values. Now the element at the ith index is this and the element at the jth index is this, right? So now we will again increment the value of I and compare it with the pivot element. Is 7 greater than 5? Yes. So I will point to this element, right? And we will decrement the value of j and compare it with the pivot element. So is 4 less than 5? Yes. So j will point to this element. But here we will not interchange the position of I and j. Why? Because I is now greater than j. This all loop will increment up to when I is less than equals to j. But when I becomes greater than j, we will stop the swapping process. And what we will do? We will swap the pivot element with the element at the jth index. So the jth index is the shortest position of that pivot element. So here the pivot element is 5 and the position of j is this one. So we will swap 4 with 5 and in this way we will get the element 5 in its shortest position. Now see, this is the array which we got and see here all the elements in the left part are smaller and all the elements in the right part of the element 5 are greater, right? So hence we can say that the element 5 is in its shortest position and the array is divided into two sub-arrays, right? Now the same process is repeated for both the arrays. So now for this sub-array we will consider the pivot element as the element 4, right? And the ith index is this one and the jth index is this one. Why? Because this is our first sublist and we need to sort this array. So this element 2 and 4 will get swapped and our array will look like this, right? This is our left subarray, this is our previous pivot element, and now so in this array if the pivot element is 7 then the index I will start from this position and j will start from this position, right? So 9 is compared with 7. Is 9 greater than 7? Yes. So now from this side 12 is compared with 7. Is 12 smaller than 7? No. So we will decrement the value of j and compare 14 with 7. 14 is again not smaller than 7. So we will again decrement the value of j and we will compare the element 9 with 7. Is 9 smaller than 7? No. So we will again decrement it. So now there are no remaining element to be compared, right? So 7 will be stored in its own position only. Now see, the 7 got stored in its own position only. So now our sub array is this part, right? As this part is already sorted. So in this part, let the pivot element be 9 and the value of I will be 14 and the value of j will be the element 12, right? So we will compare 14 with 9. 14 is greater, so I will be here only and we will compare j with the pivot element. So is 12 smaller than 9? No. So we will decrement the value of j. Now 14 is compared with 9. Is 14 smaller than 9? No. So we will again decrement it. But there are no remaining element as we have reached 9 itself. So we will swap the element at the index I with the index j and we will get our final sorted array, which will look like this. In this array, all the elements are in their sorted position and hence the array gets sorted using this quicksort technique. Now here is the algorithm for this quicksort technique. This dividing process is written within the function partition, which takes the argument the array, the lower bound and the upper bound. In the beginning, we are setting the variable I with the low plus 1 and j with the up, that is the upper bound. We have just seen here I is low plus 1, that is 0 plus 1 equals to 1 and j is the upper bound. And we are setting the pivot element as the element at the lower index, that is 5, right? Now we will execute the loop while I is less than j. Now we will compare the pivot element with the element at the index I. If the element at index I is less than equals to pivot, then we will increment the value of I. And while element at the index j is greater than the pivot element, we will decrement the value of j and we will move towards the left side, right? Now, when the condition 1 and 2 are not satisfied and I is less than j, then we will swap the value of the element at the index I with the element at the index j and we will increment I and decrement j. So in this way, we had swapped the element at index I and the index j. Now, if this condition becomes false, that means the ith index becomes greater than the jth index, then this means that we found the proper place for the pivot element and it is given by the index j. So now we need to place the pivot element at the jth index, right? So we will swap the element at the jth index with the element at the lower index. That means lower element is nothing but the pivot element. So we will swap both of them. In this way, the pivot element gets its sorted position. Now we will return the value of j. That means the position which is the point for partitioning the list into two sublists. So this is the block for the function partition. Now where the control of this return statement is going? It is going in this function quick. What we are doing in this block? Here we are partitioning the list into different sublists, right? So while the lower bound is less than the upper bound, we will call this function partition and this index j will be stored in the variable log. That means the variable log contains the index of the element from where we need to partition the list. Then we will call the same function on the array A and it will be called from the lower bound low and the upper bound log minus 1. That means we have just seen if this is the position of partitioning, then we will call the same function for this block. So this is what? The low, that is the 0th index, and the log minus 1. That means the index at the element 5 minus 1. So this is the function call for sorting the left sublist. Similarly, this is the function call for sorting the right sublist. So when these steps are executed repeatedly, then we will get our sorted array. I hope you understood this quicksort technique. Now let's see the complexity of this quicksort technique. So the time requirement of quicksort depends on the relative size of the two sublists formed. We can say that the partition is balanced if the size of the two sublists will be equal or almost equal, and speed of sorting algorithm in that case will be fast, and the partition is unbalanced when one sublist is much larger than the another one. In that case, the sorting operation becomes slower. So, the best case arrives for this quicksort technique when the pivot element is placed at the middle of the list. That is, we get two equal sized sublists. Right. So, if the position of the pivot element would be found in the middle index, then we will get two equal sized sublists. So, this is the best case. So, in this case, after dividing n elements into two sublists, we will get two sublists of n by 2 elements, right? When we will divide, we will get two sublists, the left sublist and the right sublist, each containing the element n by 2, which are again divided equally to form four sublists of size n by 4. So, when n elements are repeatedly divided into half, then we know it takes the complexity of log n time, right? And then we will get n sublist each of size 1. After many divisions, at some time we will get each sublist of size 1, right? So, for one element, if the complexity is log n, then for n element, the best case complexity will come out to be n log n, right? So this is the best case complexity in big O notation. Now the worst case. Now for the worst case, consider the scenario in which we choose the element as pivot which is the largest or the smallest. That means when the pivot element is either the largest element or the smallest number in the list, then it will be the worst case. And after partitioning such a list, we will get two subarrays. The first is an empty array and the another containing n-1 element. This is something very logical, right? If the pivot element is the smallest or the largest element, then we will get an empty array and another array containing n-1 element. So, an array containing n element, when it is divided into two sublists, we will get two subarrays, one of size 0 and another of size n-1. Now, if the array is in reverse sorted order, that means if we want to sort the array in ascending order and the array is inputted in the descending order, then when we again subdivide this list, we will get again two sublists, one of size 0 and another of size n-2. Similarly, after subdividing again, we will get two sublists, one of size 0 and another of size n-3. So in this case, we will get total number of comparisons as n-1 plus n-2 plus n-3 up to 1. So this will give us as n into n-1 by 2, and this is equals to order of n square. So order of n square is the worst case complexity in big O notation of this quicksort method, and the average case complexity is also equals to the base case complexity, and that is order of n log n. So I think I am able to clear all your concept regarding this quicksort. Still, if you are having any doubt, you can ask me in the comment section. And if you like this video, please subscribe the channel and tap the bell icon to get the notification about my next videos. Thank you.